Welcome back to High Performance Computing, Lecture 2, Parallel Programming with MPI, and our second part. So the first part was talking about really core basics on MPI. So the question was at all, why should we care? And why this is now related also to C programs. So we made of it the elements in different applications, making it feasible to think about these topics. So many of the scientific and engineering applications today, they really are C++, C applications, maybe even Fortran, right? And so with this, we have the base for many of these, let's say, natural phenomena we want to understand, or we have seen also better crafting of aircraft or airplanes. So all of these have questions which are really computational complex, and one processor is not enough for it. That's what we did also in the introduction of the course already. So maybe not even the processor in computing power is a problem, but also memory. Hence, we have a possibility with MPI then to extend this memory and extend the possibility of using different processors really to an application program. Hence, we switch from serial programming to parallel programming. This has several challenges, as we also will now see in the second part, and it's not at all the most trivial thing to do, because also if you think about higher and higher scales, there are other factors that can hamper your performance. So while I here show you, well, we can scale from 1 to 2 to 4 processors, and in some of the application examples, maybe to 512 or 1024, there are applications in the thousands of processors used. And you will see with Amdahl's law later in lecture 3 and other, let's say, lectures coming up that there are certain other limits. Hence, parallel programming is something where you often need also a sort of understanding on the basics, which we will carry along now, but also a certain understanding of the hardware or a certain understanding of what we also call performance analysis. So we will see that there are some bottlenecks when you do parallel programming. This is a topic we carved out over the last couple of years more and more in order to give place for AI. So in one respect, we should probably also have more and more, let's say, courses on HPC on AI and HPC on, let's say, more physical simulations. And we put that all here in the course, so we sacrifice some of the lectures. But parallel programming goes along also with something we called performance analysis and MPI performance analysis as well. So from the basics you learned then in the first part, like collectives, which are different, let's say, from point-to-point communication, we will move now a little bit to the overall idea of MPI, to basically thinking about the environment. So from where to where we think about a parallel execution, something which we call MPI init and so on, and MPI finalize. And then also elements where everything is not always computing, right? And message exchanges, there's a lot of I/O in these parallel applications. And hence, one of the major themes also in this second part here, when we talk about MPI, is also MPI-AO. Needless to say that this is a conceptual lecture. So many of you will say now, well, we miss a little bit of source code examples. There will be a practical lecture 2.1 that will basically be alongside this lecture, also to reacting some of the student feedback of saying, well, there's quite some repetitions of lecture 2 versus lecture 2.1. So we really condense this year a little bit of saying the practicals are in the practical lecture 2.1, as the name suggests, while we keep it here more to the conceptuals of MPI at large. So fasten your seatbelt for another tour to MPI on different facets. And the first thing is really understanding, again, this parallel environment. We always have to think about that this is just a specific space where processors know what role does this one processor play in a bigger picture, right? If you don't have this, and you see that a little bit here, in the area where we called it maybe the serial part of the code, right? This is all source code. Let's say a C program, we have the MPI include file, but that doesn't make it parallel. So we have done prototypes, we have declarations, then somehow the C program begins, but it's still serial code. But there are some certain statements, and this is the MPI init and also the MPI finalize. here that we have, where we have the parallelization that can take place through this message passing involving all the different processes I have, let's say, to my disposal. Now, another thing I wanted to bring across with this slide is that usually what we do in a parallel environment is we program the code as if we don't know how many processes we might get. And this is an explosive statement, both, I mean, in terms of how much I get, but also how I do this. When we think about practical lecture 2.1, because this is now depending on an external element called the job script. If you remember, we had practical lecture 1.1. In the job script, I could steer how many times something should be executed, how many processes I want. So this is something I steer from an external element, which is a job script, and should land in my C executable. And this is a bit now the MPI environment. It will be knowing what exact number of processes you have at your disposal by asking the scheduler, and that makes now the picture complete altogether, to say, this is the amount of process you have now. But if you specify something else in the job script, let's say instead of 12 processes, you have 10, you have 8, then you have just those. In other words, we're talking about having always the same source code, being able to dealing with an amount of processes we don't know, right? So you would not code towards, I mean, we always know, hopefully there will be more processes, right? So in an ideal case, maybe even more and more, although we see, of course, many applications have some limits, like the data itself is maybe not enough to put in memory anymore, or it doesn't make sense to really use that in so many processes because the computing is so trivial at some point in time. So there are certain limits in scaling. We will come to this a bit when we talk about different scaling laws, and this also brings back the point of Amdahl's law and so on, and Gustafson's law, things we will basically hear later in the course on parallelization fundamentals. But this is an important now part to understand this ... here, right? In this center of the slide. Seems trivial, but for you to understand, this is alluded a little bit to the point that we want to program a parallel program in a way without knowing how many processes I will get. So from the more implementation perspective, also I brought across in some abstract ways already the buffer, right? And many of you are not maybe directly familiar with the buffers and so on. It's something more related to C. Maybe when you have essentially, let's say, data you want to send over the network, which is in one variable. In order to send it over the network, you would have a buffer using that to receive it basically at the other process, because there's essentially no space for it. Hence, you need a buffer to make space for it, to then overwrite, let's say, your variable you have maybe already set across. But in that time where you do the messaging, you will see you need this certain type of buffer, right, to bring it across the network. And with this is a much more detailed view on all the message exchanges you see here, which can be misleading, I admit that, because you have seen there's also, for instance, a broadcast, right, to many others, or a gather, from many others to me. So this is just more to get you more and more aware of the parallel environment and what message passing plays there. And the source code then, of course, will make it very detailed in practical lecture 2.1, where we then really allocate buffers, where we use them in message exchanges. We keep that out here to really focus on the conceptuals. Now, another interesting thing is when you have the MPI program, and a little bit, this was already in the Hello World example that I had the last time, right? It was very easy, Hello World, that's it. So, and we could execute it a couple of times. I did sbatch, if you remember, a couple of times with the job script. We got a couple of times Hello World independently, right? So independently means it was just a program, executed, done. Now, what this slide brings across you a little bit is this difference in terms of awareness and output. Do you see one interesting and very important addition to this, right? Which also sells, it says a bit the stories of solving a problem in a cooperative way. Of course, Hello World in a cooperative way. It's a tutorial. It's the first, let's say, training lectures in MPI. But think about it, that every of the processes that you have now, when you use this MPI, will execute the hello world, no doubt, and will bring a beautiful output, but it has a certain awareness that actually I'm one of four, right? And this brings back this idea of ranks that I brought across in the first part of the lecture today. So the MPI environment, when you have initialized it properly and will execute the job with MPI run, for example, the schedule will make sure to schedule that on different processors and will bring back to the MPI environment that you have, let's say, asked for 4 processes in the job script. Hence, the processes that know, although they're completely independent. Now, that's important, right, to understand. In a way, it's, of course, one MPI program on 4 processes, but they still run their source code as it would be basically independent. So hence, they still, with a rank, they have an awareness that I'm just 0 out of 4, or I'm 1 out of 4. So they have a certain identity. And this will be an important part later down the road when we have more complex applications. We will start already in practical lecture 2.1. If you think about the simple ping pong between these two, right? You would say you need an identity. Who is implementing the ping and who is listening for the ping, and who is actually then implementing the pong and who is listening to the pong. So basically, this is something which will be the first, let's say, more elaborate application example, if you want, between Hello World and the more application example. But this is now important to realize that this is what MPI brings you as an environment. And of course, this is in collaboration with the scheduler, right? Because the scheduler then that we learned in lecture 1.1 will be the one that says, you asked for 8, there are no 8. Sorry. So in this sense, your job will wait until there are 8 processes, and then you get what you asked for. Alternatively, many others have asked for 16 processes, and you come along and, I just need 4, and the scheduler will say, well, there's a whole of 4. I mean, everybody asked for 16, but there's a whole of 4 processes now in the schedule. I can schedule you now, and your job gets immediately scheduled because you just asked for 4. However, of course, it's not that simple in applications usually, right? You, of course, ask for a certain amount which scientifically makes sense, which engineering-wise makes substance to your application. Let it be the turbine we learned. So hence, this is just a more abstract way of thinking about it, but it should capture for you the benefits of using MPI in parallel on different processes, not only getting computing, not only getting more memory with distributed memory and the message passing, also the whole environment. And we will learn more about this, about communicators. So there are certain amounts of processes are grouped in communicators, as I was alluding to in the third part 1 as well. There's another way of elements, and let's say quite a fraction of the MPI standard that is talking about so-called non-blocking communication. And I think it's also important to mention this already. Needless to say, we have a small demonstration in practical 2.1, but here I was always in the beginning now in the first part and now always saying there's a send and then there's somewhere a receive, right? And if you do this, you have certain waiting times, right? Let's say the processor, which is the timelines that you see here involved in having the receive operation and a processor having the send operation, they will do this at a certain amount of time as they, basically compute. So this could be a waiting time, which is a loaded term, actually in exactly what I told before in performance analysis. This is what you want to avoid, right? Because in other words, some processes are idle. So this processor here in the waiting time, sorry for that, basically are waiting and doing nothing. It is already ready to receive, nothing happens. And then there comes an MPI send, right? At some point in time, now I can proceed, now I can work, I have the data I need from the MPI send and can work on my received data. And of course, you can stretch this across different processors. Hence, there are different ways of do also non-blocking communication where you will say, perhaps I can do something else in the time and keeping the, let's say, the waiting time smaller with some non-blocking communication, right? So that I can still do something maybe with the MPI I sent here. And However, this goes along with the MPI wait operation. So they have a different wait operation that needs to be in combination with this, let's say, non-blocking operation. And you have different really scenarios where this makes a bigger impact, also waiting, sending. So, and one way to understand it is really that the computing or what the different processes can do are not always a very extreme equal load. Although you have the same program, you maybe compete on different data sets, which are much more complex in one than in others. So one process is maybe much more quicker done and then receives and waiting for the receives a long time while the other one is still working a lot in the computing. It's alluding to a problem we call load imbalancing. And this will be something in lecture 3 we will target. So here, bear with me. We can cover everything in one lecture. But this is something where also here and there you can mitigate this, or you will see also an application example that this is often used in practice as well. So in a way that's saying a little bit how I already explained it here, the practical example, and then also the understanding of this domain decomposition is sort of essential to understand it a bit. Hence, instead of using this slide, I would rather put you an emphasis on this side, considering that you maybe have even 4 neighbors you want to talk to, right? And this brings back our example of the waves of the ocean we want to simulate. Maybe it's the coast, from UK over to Iceland here in a very coarse-grained scenario. But you want to understand a little bit what's happening on all of these different ocean tiles. And for this, you basically need all your neighbors. And this is a little bit alluding to the source code here that you can actually now exchange information between your different neighbors. And you would do so maybe with an I send and I receive, a non-blocking send and receive, because the computing itself might be very different in time, might be very different in terms of application logic even. I was mentioning that some maybe have a sailing boat, some other tiles not. Or let's say fishing. The amount of fishing might be very different to compute on one tile not. So this would help still by exchanging this information, and you would do this in every time step, right? To, let's say, give the information to your neighbors with a send. But of course, you can imagine now, if I want to compute in the next time step, my wave height, the water in my neighboring tiles that actually are swapping over, if you want, and their wave height will influence me. So I have also certain receive to it, right? And hence, for, let's say, nearest neighbor communication, this is an essential paradigm. And we will come back to this in lecture 3 when we talk about domain decomposition more, obviously. And by doing so, this is just one application example where it's, I think, more clearer why you need this sort of non-blocking communication, but also why you at some point in time basically also want to wait perhaps for all of these have taken place so that you can basically give an informed answer. You see here what I basically have received from all the different ranks from all my neighbors here, 0 to 3, basically smaller than 4, and so on. Hence, you see more and more to really understand it fully. Every now and then, source code is really a bit much more better to tell, and also application examples that I will bring in lecture 2.1 and lecture 3 then with domain decomposition. So in the moment, just be aware that it does not need always to be, a blocking send and blocking receive. I can do nothing else. So in that time where I maybe have initiated the receive, I can do something, but there's an MPI wait. If I really wait for it, that I got the send in the end. It's a bit abstract understanding, but I think also the graphics here gives you a little bit more an understanding why that is an interesting concept. Hence, the practicals will follow suit. Now, let's say another important part in this lecture, especially in the second part, should be now I/O. So I/O, input output, very trivial. Usually you would say, well, I usually have it on the screen. If not on the screen, it's in a file. Big deal. So in parallel I/O, there are certain complexities. And this has to do with the parallel nature on the processes living on their own. So basically, I told you once to think about the processors here in the HPC system. Then I told you shift the view on the networking, where I said this now makes HPC important, right? Because they have an extremely well interconnect. And now you better understand why, right? Now, basically, the interconnect is always used when I want to, talk to many processors at every time step. Let's have the wave propagation, approaching from Iceland, the UK, and other parts of mainland Europe or whatever. You would have this at every time step, having exchange of neighbor information to understand, different physical variables. Wave height is just another, maybe even fish population, whatever. So this is information again and again going over the wire. Hence, I told you shifting the view to this. This is high performance computing. This is very important. The same is true for climate, for weather prediction, right? So here I ask you again to shift now the view again, and not so much only on this interconnects, which carry the data, but also then the storage, right? So data needs to be somewhere stored. And that's where we talk about certain parallel I/O techniques that actually are adopted from many, many different applications as well, these concepts. And you will even see that more and more applications are actually sort of I/O bound. So you could even throw them more and more computing power, more and more processors, but the I/O still dominates the overall execution time. So it's more harder to read all the data every time step, so that the I/O performance is crucial for the overall performance, for most notably if you think of higher scales, right? The same is true even in deep learning. We will learn, right? If you want to, let's say, give the GPUs more and more data, you have to get the bandwidth for it, or you have to have the data for it to also fuel the many GPUs with more and more data. Hence, you would say the deep learning algorithm should be faster and faster training. Yes, we can do that with distributed deep learning, but it has limits, of course, from the available data that you can stick to GPUs, and also the speed that you can fuel GPUs with. And this is all an I/O challenge and a point I was doing before a little bit in the introduction, but we will come back to as well. You can mention that, of course, certain elements like rate levels, data duplication, replication of data, there are many topics as well which sort of play an indirect role for HPC. We tackle them more in the cloud computing and big data course, right? So where we have also, different approaches to several of the data problem. So what means I/O really is something what you see on the left side. We have some beautiful memory, very fast, lots of data to be computed. We have beautiful MPI, can exchange messages, compute, but at some point in time, the application is just ready or needs data, right? It could be experimental data that we talked about before from observations, so real life data that maybe helps the simulations to get back on track, or to have important initialization data, but disks are still sort of important. So don't get carried away that HPC just can solve everything just by more memory. Hence, we need disks, we need I/O, and this is now something where a so-called parallel file system also becomes an essential part of it. So something like Lustre and so on. So there's specific file systems that basically treat the concurrent access to a file as a common event, right? So again, concurrent access to a file from different users as a common event, or from different processes, really, right? So hence the parallel file systems are made, as the name suggests, for parallel access to files, to data, and that's what we're going to learn basically in the next couple of slides, how that is realized and why this is so challenging, right? And another point in this is, of course, that although it suggests that just put more capacity, more storage to it, and you see here also storage robots, right? You see here tape archives, getting into something we call tertiary storage, where you then have huge capacity, but it's incredibly slow, right? To migrate or basically files back to your disks takes a lot of time, especially if many smaller files. Hence, you cannot just run an application and then assume that you get many terabytes out of a tape robot, So this is one of the pattern aspects of it. Another one is, of course, that you have then still the network interconnectivity between the different nodes. That means not all of these nodes are maybe one-to-one with a perfect line interconnected. You have something like tree networks, and nowadays also dragonfly networks. Things we also don't tackle in this course intensively anymore. We talked about this in previous iterations, but because of AI, we also had to sacrifice some of the topics. Hence, the I/O is also a bit dependent on the network interconnect, right? So how well is that? Are there certain I/O nodes that play a specific role that we have seen, for instance, the blue gene, systems I/O nodes that handle I/O for many different processes? And of course, they can quickly become a bottleneck if you have an I/O intensive application. So you see more and more is, this I/O a challenge in MPI applications. And the most dominant challenge, if you want a little bit, is probably how you access a file. Many of you know that from your serial processing on a laptop. You have a text file open and you open it up again, right, on a laptop. So you would have twice the text file open. So when you edit it in one editor and you don't save, then you go to another editor, you sort of have a problem. If it's a smart operating system, what I think the laptop will actually tell you something, will say, well, this text file has been edited, or this text file is not saved. Do you want to save it before the other text editor edited? So we talk about a serial access, right, to a file done by one thread on your laptop. Here we have the same problem of serial access via one process that I think is trivial to do, right? So it opens the file, writes to the file, or reads from the file, done, closes the file. So shared access via multiple processes. Now, if you think we run 512 processors in parallel and all have to have the access to the file, write to the file in parallel, the shared access is, of course, now a challenge. And this is where, basically parallel I/O comes in. That's where parallel file systems are good in. They storage, let's say, the single file basically more distributed in something we call file blocks. So in the end, you have to think about this is also then giving you the scalability, right? So that we have many different file blocks of potentially, many different, bytes, terabytes even or so. So advantages is then that, you have this combined bandwidth of all the network to it and the physical drives, right? By having these different file blocks that many processors have still, let's say, different access to it, although logically it's still one file, and we will make the case in one of the slides for it. Of course, then the disadvantages, it's, the file system in a way then just stores blocks. And if there's, let's say, one block lost, could be, let's say, vulnerable to problems, disk failures that actually happen in the HPC center almost so weekly in a large center. So there are different areas where you can improve this. And one of it is then the redundant area of it, inexpensive disks, the RAID systems with different levels, where you then have to think about how much you store versus, the benefits you get of getting your data safer and safer. So this is one way of doing it. And examples of this parallel file systems then to, let's say, treat concurrent access to files and rather as a normal point would be in the past maybe GPFS, and which has been now renamed to EVM Spectrum Scale, developed by EVM. So not, let's say, directly an open source solution, but there's also Luster as an open source solution that is often used these days, which essentially is then a parallel file system that really supports on the file system level our MPI applications. And there's also MPI I/O that I want to bring across that then leverages these functionalities. There was also PVFS quite known in the past, although I have to say Luster is quite commonly used today, and of course also EVM Spectrum Scale. So coming back to the logic, however, how that works. And this is an important idea because we talked about that now we have, let's say, parallel access to files. So we see this here as different threads from different processors accessing one single logical file. However, if you now, and that brings into two mappings, if you look on it on the block idea and the IO nodes that we discussed, this is going to a very distributed computing setup. And this is a key to really is now the understanding of it, why it can be having a much higher throughput than, let's say, really a single physical file, right? Because otherwise then one thread has to wait for another to write, and then another has to write. And if there are 256 or whatever, 512 processors that want to access one file, or even thousands, then you are in deep trouble. Hence, this mapping of blocks and compute nodes is an important factor, where we basically also striping through the different available possibilities. And this striping is a little bit shown here, two different IO nodes in terms of the logical file. So certain areas are always mapped, with a striping technique to one IO node or to another. And for the application domain scientist, or for the people implementing MPI, it still looks like a logical file, but underneath, let's say, parallel IO and the IO libraries take care of quite some mapping to really get it in a distributed fashion, right? So hence we should call it a parallel and distributed file system in a way. Distributed not because it's distributed among many hosts, so not on the internet on location A and location B, but rather on different locations within your storage system. And you see here one of it that we had in Jülich. This is just not computing, this is storage, right, in all of these different racks. So showing you also that computing is not always about CPUs, GPUs, it's really about data as well. Hence, our complementary course is called Big Data, Cloud Computing. These are all topics very close to each other. Hence, with the shift the view, we have done this interesting facets of saying data is important, and we still have to have the point that also the network topologies are important, right? So usually you would have, when you have now MPI I/O, maybe a torus network that you see here. That means every processor is very nicely connected with its neighbors, supporting a little bit what we have seen across the ocean, right? At every time step, I want to get information from my neighbors, and they are just, let's say, from the network interconnect, always directly connected to me. However, some implementations maybe have rather, if you want to see here, a tree sort of network with oversubscribed connections. So not everyone has a full, let's say, bandwidth to the other processor, which is not a problem for toy examples I have here in the course. But if you have a real big application, this can be already creating quite some bottlenecks. However, coming back to MPI I/O, you see how that works a little bit in the bigger scale. We have communication. You learned a lot collective and point-to-point. We said a little bit with weight, right, with non-blocking communication as well. There are some ways of synchronize. And then with MPI I/O, we entering a new facet of MPI. And that's what I want to do in the last couple of minutes. However, take away the message that there will be also practical lecture 2.1 examples. And some of them are so easy to understand that we can go relatively quickly, I think, through some of the examples. Also to contrast it now, what might be more performance or less performance. So MPI I/O in principle means we have done something in our timeline as a processor, and I have a result I want to store. Right now, immediately come to think, okay, then I have my own disk, I store something. Same for processor 2, I have my disk, I store something, and so on and so on. So in a way, now when you see the anecdote, and this is also one point of the slide, it is a bit similar than maybe sending messages to an I/O device, right? Hence, if you look on the MPI I/O standard, it looks a little bit like messaging, right? Just to I/O. Hence, there's a send receive sort of understanding and also collective information that I want to put everything now to one file instead of communicating everything to all the other processes. So the API is a little bit supporting the idea of collective operations, and this makes sense because we want to scale, right? We want to use now 512 processors in parallel, and I don't want to implement now that everybody actually please store your result. is logical, right? With 512 processors, I don't want to make the effort. I just want to have one source code line saying for all processors, please write all your results now in this file. Let it be for what we call checkpointing, maybe assuming that you maybe have an, let's say, computational intensive climate operation you want to simulate, or climate simulation of some sort. It runs for 36 hours. So maybe checkpointing every 4 hours is good, because if the job fails at any point in time, you have wasted maybe 24 hours and there's an error in the last couple of hours. So checkpointing is also a very important concept, motivating MPI-I again. We don't have big slides on it. It's just a sort of more motivation around it. And MPI-I, and this is then also something we lose a little bit perhaps by bringing in more AI now. In previous lectures, we had also MPI-derived data types. So you can actually have advanced concepts to have big arrays, structs, different data structures really also sent around as messages and defined in the MPI environment. And this is something we don't tackle much more in the course. So here I would point you to basically the last couple of years. However, now thinking about I/O, what you can do is, of course, a sort of serial approach to it, right? So, and this is now needed to really understand the difference what parallel I/O is doing. So hence, don't do this. It's not that I teach this. I just say it's important to understand the difference. So when you now think about 512 processors and say, well, there's one fellow that we determine basically as a master worker concept, if you want, to say you're the master for AI, so we send you everything, you put things to file. So one process in a way takes care of all the other processes. What you can in a sense do, depending on the application logic, but obviously there's no scalability. Remember the buffers, remember it has to be all communicated to the memory before this processor then can take the memory and drop it to disk. So let's assume we have 512 processors and they have all used the memory intensively, so maximum. The processor has not even space for it. Hence, or basically he has to serialize this. So now after one after another, everybody comes, sends some data, and then write it to file. So this is something where you can imagine automatically this will take a long time, right? As it suggests, right? So you see that's the timeline here. So the first processor, okay, the second, the third, the fourth. So it is a long timeline. So this is really an increase in communication and also has lots of load imbalance risk. So everybody else is waiting here all the time until the I/O is done and continue processing. Hence, there's a smarter way to do it. And now you would say, well, that sounds of logic. Everybody is, doing it on their own, one file per process. In a way, that's what we can call also parallel I/O. It's fair and square. So you would say everybody has its own share on the AI, on the I/O, and then let's just drop the data we have, maybe from AI applications, reading in different data sets, sort of things. So in a way, it's also practically here and there applied with data, right? You have data parallel, but also there are different ways how to make it better using really parallel or with one file. But this is something we come later to when we learn about distributed deep learning. But when you think about traditional, let's say, sciences here in terms of physical sciences, you would have different results storing the all to different I/O on their own, let's say, disks. Might be interesting, but the problem is usually that then the file system often gets into trouble. For instance, the number of inodes that are then available on the file system, right? Because many different files, let's assume we run it for 25,000 processors. That means at one point in time, we create 25,000 files at once, right? Because everybody has its own file, everybody has its own thing to write in, but the file system remains the same, right? It's all for one, the file system. So hence suddenly dealing with, for instance, Linux derived derivatives are usually on HPC systems. So the inodes, which is a concept then storing all the information about files, directories, and so on, is then, let's say, in a serious trouble creating all of these files. Hence, we call that a bit the sort of contention with the file system. It's also not really scalable, this parallel I/O, although it sort of suggested by the way of doing it. So, but the way really to really scale in a way would be then the shared file. So this means that, of course, every process each performs still its I/O. So obviously I have my memory, and in my memory are all the results from the data I want to store. I have computed, I have exchanged messages, physics, whatever it is. And now I have lots of data I want to store, but I do so with this one big shared file. And in a way, you would also say file pointer, right? So in previous courses, we were going a bit more, closer to the details with so-called file pointers within the disk that you basically need in order to know, to write this logical file and so on. So hence we're talking here about that this is, feasible in terms of scaling. However, obviously, when you have many processes, and now I'm leaving the thousands, but rather talking about 10,000, 100,000 processes, this gives still some contention of file systems, right, for several different purposes. But this is something where this MPI-I then would take the way of programming of saying, let's have a collective operation, right? Something that almost like, sent, like the broadcast operation, sent to everyone. But instead of broadcast, I want to write, right? But every process is involved at that point in time to write the status. For instance, for checkpointing, right? It's now 4 hours of computing. Let's make some checkpointing. Where are we with the weather, with the climate? So, and then continue processing. So in a way, then the current result is put as parallel I/O into this disk. And this is an enormous benefit in terms of time. And obviously, it's just a conceptual idea here of the course. I will give you one example in the practical lecture 2.1. But how it is used is also with significant extensive options of so-called higher level libraries, right? You will see that the way how it works with applications accessing I/O hardware is truly not just the parallel file system. Usually you have a high-level I/O library like HDF5, for instance, these days, or NetCDF, which really have different facets that we will only cover a little bit in this course here, because also that is something we sacrifice a little bit more in terms of getting AI in. But this works together with the, let's say, runtime of MPI-I quite well in order to abstract them from the parallel file system in ways that you see you can still program, let's say, the I/O as it would be message exchanges to the file almost, right? So write, read, and so on, but collectively across many different processes. You don't want to do this for each of the processes. And then if you have a certain standard how to write this information, right, is another point. Data structures, hierarchical data format can be seen a little bit like a file system in a file, right? So you would say you have slash something, slash data, slash names, slash phone numbers, slash. So you would have within one file an idea of a file system. For example, NetCDF is good with arrays, multidimensional arrays used in climate weather simulation. So they have all their modus operandi. If you want even a certain community standard behind it. And to abstract from this, they base on the I/O library from MPI in order to make the read and write happening in a scalable fashion. And this is, I think, the most key elements I could bring you across from MPI at large. Admittedly, leaving many things. One of it is LGATher that I didn't cover, but it will come back to us when we talk about deep learning, right? So hence, I would also encourage you to look a little bit on this video. It nicely summarizes, again, serial versus parallel, and also this different, let's say, communication paradigms we have seen. So we continue with practical lecture 2.1 with really bringing source code to the game, doing some practical examples on a HPC system, using schedulers, asking for different amount of processes, which is the other part of the story. So talk to you then.